So we're going to go through some molecular geometries today. There are um, 5 of them that we have to know. We have to know about the bonded angles and the lone pairs and things like that. So we're going to get right into it. We're going to start with the example of CO2. So CO2 we know is drawn with a carbon atom. It has its 4 valence electrons bonded to 2 oxygen atoms, which have 6 valence electrons. And when we connect our electrons, we have a double bond. When we go through the double bonding, our final product looks something like this. But we have to know why the shape is going to be that way. So this molecule is considered a linear molecule. A linear molecule has a bond angle of 180 degrees. What that means is from this point to this point, 180 degrees. If you've taken geometry before, you know a straight line is 180 degrees as an angle. It's half of a circle, which is 360 degrees. So we have an angle of 180 degrees. We can identify that a molecule is going to be linear based off the total amount of bonded atoms, lone pairs, and electron domains. So if we look at the CO2 molecule, we have 2 atoms bonded. We have atom number 1, the oxygen, and atom number 2, the other oxygen. So we have a total number of 2 bonded atoms. If we look at our carbon molecule has no lone pairs around it. Remember, lone pairs are those things that are on our oxygen, but lone pairs matters on our central atom. So carbon has 0 lone pairs. So our total amount of domains here is 2. So any linear molecule will have 2 bonded atoms to it. It will have 0 lone pairs, and we will say that it has 2 domains. So make sure you write something down into a notebook. You need to know the shape linear. You need to know that it has 2 bonded atoms, 0 lone pairs, and 2 electron domains. And you need to know that it has a bond angle of 180 degrees. Our next shape we're going to go through, our example for this shape is going to be the molecule BH3. So boron has 3 valence electrons. There are 3 hydrogens, each with 1 valence electron in this chemical compound. The electrons are going to pair up as such. So when we redraw it, we have boron connected to hydrogen. And how I'm going to draw it is I'm going to space out my hydrogens evenly. This shape is called trigonal or trigonal planar. In a trigonal planar molecule, we are going to measure our angle from one hydrogen to the other, which is 1/3 of a circle. So each distance, 1/3 of a circle, or 1/3 of 360 degrees, is 120 degrees. So our bond angle here is 120 degrees. Again, we can break this down based off the total amount of bonded atoms, lone pairs, and electron domains. So in this case, our central atom, our boron, has 3 hydrogens attached to it. So it has 3 bonded atoms. Our boron has 0 lone pairs around it. So we have a total of 3 electron domains. Anytime you have 3 bonded atoms, 0 lone pairs, and 3 electron domains, it will always be a trigonal planar molecule. Notice how the trigonal planar molecule is different from the linear molecule. Linear has 2 bonded atoms. Trigonal planar has 3 bonded atoms. Linear molecule has 2 electron domains. Trigonal planar has 3 electron domains. So there's a difference if we look at our bonded atoms, our lone pairs, and our electron domains, and that will help us figure out what shape we need to draw these Lewis dot structures in and the shape that the molecule is going to be. Why the shape really is important is if you think of like a game of Tetris and you're always trying to fit the right shape into the right spot, a chemical reaction is the same way. You're going to need a molecule, a specific shape that can react with another molecule in a specific shape so they fit in the right spot and they can exchange atoms or however the chemical reaction is going to take place. So make sure you have trigonal planar. That's the second geometry we're going to go through. That's the second one that should be in your notes. The third one we're going to look at is CH4, that methane that was previously discussed in the last video. CH4 carbon has 4 valence electrons. It's bonded to 4 hydrogens, which each have 1 valence electron. If we connect our dots here, carbon's going to connect with our hydrogen molecule such. So our final molecule is carbon bonded to 4 hydrogens. From our last unit, we know our prefix in chemistry for 4 bonded atoms is tetra. So this molecule is called tetrahedral. A tetrahedral molecule has a bond angle of 109.5 degrees. You would think it's a circle and you break it into 4, which would be 90 degrees. However, remember, this is a 3-dimensional shape. These aren't 2-dimensional. So in a 3-dimensional sphere, when we add 4 points to it, they can be equidistant at 109.5 degrees. So in this case, our angle between a hydrogen to another is 109.5 degrees. We can go through our same amount of bonded atoms, lone pairs, and electron domains again. So in this case, our carbon molecule has 4 hydrogens attached to it. So we're going to say there are 4 bonded atoms. Our carbon molecule has 0 lone pairs. There are no dots around the carbon once we make all these chemical bonds. So our total amount of domains, 4 plus 0, means we have 4 total electron domains. So anytime you're trying to identify the geometry of a tetrahedral molecule, you're going to find a molecule that has 4 things attached to it with 0 lone pairs, which means it has 4 domains. It's always going to be tetrahedral. This should be the third geometry you have written into your notes. The fourth geometry we're going to talk about, we're going to start adding lone pairs. We're going to use everybody's favorite compound, dihydrogen monoxide, or H2O. In H2O, we have oxygen, which has 6 valence electrons. We have it connected to 2 hydrogens, each with 1 valence electron. When we make these chemical bonds here and here, we're going to finish with a molecule that has the lone pairs of oxygen connected to 2 hydrogen molecules as such. This molecule is called a bent molecule. It looks like a linear molecule that's been bent. That's the only difference visually. Our bond angle here is 109.5 degrees again. So our difference from here to here is 109.5. Yes, those electrons make a difference. These right here that I'm circling, these are called lone pairs. That means the oxygen has 2 electrons that have a negative charge, so the negative charge of those electrons are going to push against the negative charge that hydrogen has. Remember, things that have the same charge are going to push against each other, just like magnets. So those negative charged pairs of electrons are going to push against the hydrogen molecule and kind of make them separate at that equidistant angle of 109.5 degrees. If we look at our bonded atoms, our lone pairs, and our electron domains, we can see that this one's going to be different. Our linear molecule has 2 bonded atoms to it. It has 2 lone pairs around it. So the total amount of domains here, 2 plus 2, we still have 4 electron domains. If we look at our picture of water or H2O, we see that there are this domain, this lone pair that's acting with its electrons to push against stuff. This one is acting. This hydrogen still has electrons, and this hydrogen still has electrons. So there are 4 domains or 4 different areas around this oxygen that we can find lone pairs. Lots of people like to draw water like this. Which is incorrect. If you draw your water like this, I will mark it wrong. The reason that this right here is incorrect is that this looks like a linear molecule, right? And if we give it the lone pairs that we already have anyways around the water molecule, the difference is if you have 2 bonded atoms, these hydrogens, and you have 2 pairs or 2 lone pairs, it has to look bent. It has to look like those lone pairs are pushing against the hydrogen molecules. So this would be an incorrect drawing right here, and I would count that wrong on a test or a quiz or on an assignment. If you have a bent molecule or an atom or a compound with 2 bonded atoms and 2 lone pairs, it should always look like this, a bent molecule. The final geometry we're going to go through, the example I'm going to use is pH3. So if we look at our periodic table, we know that P has a total of 5 valence electrons. H has a total of 3 valence electrons. If we're going to make our chemical compound and connect the dots, we'll connect dots here, here, and here. So if I redraw this molecule, I have P. It has its lone pairs connected to an H, and an H. This one is called trigonal as well, but instead of planar, this is trigonal pyramidal. In a trigonal pyramidal model, if we're looking at the angles between these, there are 4 angles, so our equidistant angle has to be 109.5 degrees. So our bond angle is 109.5 degrees. If we're looking at our bonded atoms, our lone pairs, and our electron domains, we can see that this phosphorus molecule has 3 hydrogens attached to it, so it has 3 bonded atoms. Our phosphorus has 1 lone pair. It's this pair of electrons sitting at the top. So we're going to say it has 1 lone pair. If it has 3 bonded atoms and 1 lone pair, we're going to say we have a total of 4 electron domains. So anytime you have 3 bonded atoms and 1 lone pair, you're always going to have 4 total electron domains. If we're going to work through an example on these, and I were to give you an unknown molecule, let's say we have the molecule of SCl2. We have sulfur. We know that sulfur is going to have a total of 6 valence electrons around it. And we have chlorine. Chlorine has a total of 7 valence electrons around it. Because sulfur has more unpaired electrons, it will be our central atom, and we are going to connect our dots here and here. If we redraw this molecule, we have sulfur connected to chlorine, connected to chlorine, and this sulfur still has 2 lone pairs around it. If we want to break this down for bonded atoms, we have 2 bonded atoms, chlorine and chlorine. If we want to break down our lone pairs, we have a set of lone pairs here and a set of lone pairs here. So our total amount of electron domains is going to be 2 plus 2, or 4 total electron domains. If we refer back to the 5 geometries we've gone through, we can see there's only one geometry that has 2 bonded atoms, 2 lone pairs, and 4 electron domains. So that means that this molecule must be bent. On the packet that you're working through, you should be able to complete the columns related to bond angle and molecular geometry now, drawing the correct shape for each of the molecules. Be sure you pay attention to your bonded atoms, your lone pairs, and your electron domains to help you figure it out, and make sure you're drawing your Lewis dot structures correctly. I don't want to see bent molecules drawn as linear molecules. Those are counted incorrectly.